Okay, so hello and welcome back. So now let's do a couple of exercises on a couple of topics, and these exercises are mostly related to series parallel circuits. And let me see, the chapter over here that I have is direct current analysis, meaning that the current going through the current going through parallel circuits, series circuits, and things like that. So these are all useful things that you could know in basically in DC circuits, right? So first of all, suppose that, first of all, question number one, basically, now I'm going to actually talk about these as far as I can. Some of these are concepts, so we can talk about them. Otherwise, there's a question and we will solve the question, right? So basically, first of all, you've seen those holiday lamps. There is a string of lamps, those very small lamps in a string put together, and then it's like a rope that you can tie around anything. For example, tie around a Christmas tree, and then there is a plug that you can plug into the wall outlet, and then the whole string will light up. And of course, it's not much about the light, it's about the ornamental basically aspect of the lamps. Of course, you know, I don't exactly know what they call that, holiday lamps or Christmas lamps or things like that. I think Christmas lamps or Christmas lights. So those Christmas lights, of course, not all of them, but I would say probably 95% of them is a bunch of lights basically put together in series, meaning that you have a lamp over here. This lamp is connected to another lamp. This lamp is connected to another lamp. This lamp is connected to another lamp, and so on and so forth. And you have probably, I don't know, about at least 50 or 100 of these, and then the whole one end of the two ends of the lamps then is connected to AC, for example, 110 volts or basically 220 volts or 230 volts, and so on and so forth. These are all in AC voltage. And of course, you know that when you have a lamp, you can connect it to, as long as it's one of those, as long as it is basically what do you call those lamps? It is called a conventional lamps, right? Incandescent light bulb. That is actually incandescent light bulb, right? So it's called incandescent light bulbs. As long as you have this kind of lamp, you can connect it to either DC or AC. It works. I mean, as an experiment, of course, you can do this. You can, for example, if you have a 12-volt incandescent lamp, you can connect it to 12-volt DC or 12-volt AC. It works. and I think it doesn't really matter whether you connect it to AC or DC. You will get the exact amount of light, whether you connect it to DC or AC. I have actually done this before, a long time ago, of course, when I used to do experiments in electronics when I was a kid. So these lamps are basically in this manner. Now, you can, of course, you know that basically every one of those lamps has some resistance, right? Meaning that this piece of wire that you have here in the lamp, this is actually a resistance. It's probably around 1 to 2 ohms or so. And if you look through the filament, the lamp the part that actually lights up, that part is actually not a straight piece of wire. It's a wound piece of wire. So that means that basically this length you have to multiply it by the circumference of each of those circles that have been put together in order to give it this length of filament, basically. And it's also interesting to note that basically this kind of lamp actually gives you light because of the heat, not because, electricity passes through, the electrons pass through this filament. This filament, as a result, gets hot. When it gets hot, this material, whatever that is, I don't know, it gives off light, and that's how it works, right? Even today, I do use the same type of lamp, because other types of light, I just don't like them. I have, for example, in my room over here, I have one of those 60 watt, for example, the same type of lamp over here on this below the ceiling. I have another lamp over here on top of my head. Other types of light, meaning that LED and that sort of thing, I don't use, because it's just not, when you compare them, you will actually see that basically the light coming from an LED or a fluorescent basically lamp or a CFL lamp and things like that, they actually hurt you. They hurt your eyes, so it's just not a good idea to use them. So now, long story short, these filaments, you can think of them as resistors because they are resistors. They have, if you put an ohm meter on the two poles of the lamp, you will see some resistance there. So you can think of that as basically all of these resistors in series. Right? You can think of all of these resistors in series, probably 100 of them. And then if each of those resistors has 1 ohm resistance, then 100 times 1 is equal to 100 ohm, and 100 ohm on for example 100 ohm on 220 volts would be basically something about I is equal to V to R. So that would be 220 volts by 100 ohm. That's the same thing as 2.2 amps. I think the resistance is actually higher because these lamps would not draw more than at most I probably 200 milliamp, 100 milliamp or something like that. But anyway, that's how they work, right? That is how they work. And now you might have seen that these lamps, if one of them basically if one of them is damaged, then the whole string goes out. I mean, the whole string will not, one of them goes out, the whole string goes out. And then usually what people do is that you have to check one by one which one is faulty, and then take it out and then replace it with a new one, and then again the whole thing again starts lighting up, right? Which means that basically, for example, if this lamp over here, if this goes out, that means that over here you will have basically infinite resistance here, meaning that it's an open resistance, completely open, and so the circuit is actually simply open, and so no current going through the circuit, meaning that none of these lamps will actually light up. Now what happens here is that some people know this, and when one of these lamps is damaged, then they short out these two poles over here. They short this out because the lamp is not connected anymore. The lamp is basically open now. Is an open circuit now. So then they connect the whole string at these 2 points. They short circuit these 2 points, and then that means that the current can still go through the circuit. But now the difference in the circuit would be that basically so this resistance is replaced by a jumper, right? A jumper means zero resistance, basically. Ideally would be zero resistance. And zero resistance meaning that the resistance of the circuit has been decreased by some amount. Since the resistance of the circuit has been decreased, then you know that basically V is equal to I times R, and basically voltage is the product of current and resistance, meaning that in this relationship, if current goes up, resistance has to go down for the voltage to remain constant, or basically the other way around, right? Which means that if the resistance is decreased, then basically the current has to increase, because the voltage does not change. The voltage always remains 220 volts or 110 volts or whatever the voltage might be. Which means that if you take any of these lamps out, depending on the number of lamps that you take out, the current starts increasing and increasing and increasing to the point where basically the current in the circuit goes so high that basically the rest of the lamps cannot withstand the current going through the circuit, and as a result then a couple of the lamps, or one of the lamps at least, will get damaged, right? Because of the high current in the circuit. Because any lamp that you might have, it has a safe current rating, meaning that of course the current rating is not actually specified on the lamp, but any lamp can withstand at most a specific amount of current. Higher than that the lamp will actually become an open circuit, basically. So that's all about this Christmas light, right? That's all about this Christmas light. Now, the next thing that we have here, of course, not all of these questions are about Christmas lights and things like that, but this is in and of itself an interesting DC circuit. Of course, although that was not much about DC, but in many respects, DC and AC are very similar. Unless, keeping frequency constant, not playing too much with the frequency, DC and AC are actually the same things. Okay, so now let's do a couple of questions related to basically series and parallel circuits. These are simple questions that we can do in a short amount of time. So for example, let's say that you have 4 resistors connected in series across a 6-volt battery. So you have basically these resistors here in series, okay. And this is a power supply. So you have your power supply here. So let's say that this is positive, this is negative, and this is your current. This is, for example, R1, R2, R3, and R4. The value of these resistors are 10 ohm, 20 ohm, 50 ohm, and 100 ohm. You want to calculate the voltage across R2, V of R2. So of course you know that when you put these resistors in series, as with the case with the Christmas light, the voltage is going to be there is a certain voltage drop across each of these resistors relative to the resistance of that resistor. Meaning that, for example, if you have, suppose that you have, for example, these 2 resistors in series. For example, this is a circuit of 2, for example, 250 ohm resistors. And this is for example, this is your V of S. Now, since both of these resistors have the same values, the voltage across this resistor R1 and R2, V of R1 would be equal to 1/2 of basically the power supply voltage V of S, and V of R2 would be equal to, again, 1/2 of V of S, exactly the same in the same ratio, because the value of the resistances are the same, right? They are exactly the same, 50 ohm and 50 ohm. Of course, in real life, that doesn't really exist, but well, mathematically it's correct, right? Now, if one of these resistors were a 25 ohm resistor, for example, now keeping the whole resistance constant, suppose that one of these resistors, I change it to, for example, 25 ohms, and one of these resistors, I change it to 75 ohms. 25 plus 75 is 100 ohms, 50 plus 50 is 100 ohms. And V of S, supposing that V of S, I don't change it, what happens is that, of course, the current remains the same, because the voltage is the same, the resistance is the same, the current remains the same. But the voltage drop across these resistors will change, because the value of those resistors have changed. Meaning that the voltage across this resistor becomes basically 1/3 of basically 25 divided, or 1/4 of 25 divided by 100, which is 1/4 of the power supply here. So if I call this R1 and R2, V of R1 would be equal to 1/4 of Vs, and V of R2 would be equal to 3/4 of Vs. And you can see that 1/2 of Vs plus 1/2 of Vs would be the whole Vs, because that would be the voltage drop across the 2 resistors. And of course, that should of course always be equal to the supply voltage, because the supply voltage comes to these points A and B. And the voltage drop across both of these resistors is the voltage drop across the points A and B, and so that's equal to Vs, and that's one of the Kirchhoff's laws that we studied before. So there you have, basically you can see that the voltage drop across this resistor and this and the two resistors, if you add them together, you'll get the supply voltage, because 1/2 of Vs plus 1/2 of Vs is equal to the whole Vs. Again, in this case, you can see that 1/4 of Vs across this resistor and 1/3 of Vs across this resistor. 1/4 plus 3/4 is 4/4, which is equal to 1 Vs, which is the whole Vs. And as you can see, basically the higher the value of the resistance, the higher the voltage drop across that. Meaning that, for example, when you have a 75 ohm resistor here, that the voltage drop across that is 3/4 of the Vs. But if 25 ohm resistor is only 1/4 of the Vs. And the reason for that is that basically 25 ohms would be 25 out of 100, which is the total resistance there, which is 1/4. And 75 hundredth out of 100 is 3/4. 3/4 basically divide, I think 75 hundredths is of course 3/4 if I'm not mistaken. Sometimes I make mistakes in calculation. So 75 hundredths is equal to 3/4. Okay. So that's basically that, meaning that the higher the value of the resistor, the higher the voltage drop across that. Now the reason for this is that the reason basically that the reason why I'm using this ratio of the resistance to basically R1 to R of total, I'm taking this ratio and multiplying it by the V of S, is that, well, that you can just simply apply the Ohm's law to this circuit, meaning that the voltage drop across this resistor R1, if I apply the Ohm's law over here, you know that V of R1 is equal to I that is going through the circuit, which is in this direction of course, times basically times the resistance, times R1, right? So now this I is the total current going through the circuit. So the total current going through the circuit, if I apply the Ohm's law to the whole circuit, I'll get V of S is equal to basically the total resistance in the circuit R of T times basically I. Call it I, for example, this I. R of T is the same thing as R1 plus R2. R1 plus R2 times I. And that is V of S. So that means that then I is the same thing as V of S divided by R1 plus R2, right? So the current going through this circuit is V of S divided by R1 plus R2. Now, here we said that basically, somewhere we said that V of R1, here we said that V of R1 is basically I times R1, right? So that means that I can write V of R1 is the same thing as I, which is V of S divided by R1 plus R2 times R1, right? Which means that then V of R1 is the same thing as R1 times V of S divided by R1 plus R2, which is the same thing as R1 divided by R1 plus R2 times V of S, which is a ratio. So V of R1 is basically this quantity over here. which is basically simply the ratio of the resistance of the R1 to the total resistance in the circuit times the power supply voltage, right? And by the same logic, what you will get is that V of R2, for example, is equal to R2 divided by R1 plus R2 times V of S. And of course, please note here that this is a series circuit, right? This is a series circuit. In a parallel circuit, of course, this kind of thing actually never happens. Meaning that if you had two resistors here, for example, suppose that this is R1 and this is, for example, R2, and if you connect them in parallel to a power supply, of course, V of S, and so V of R1 would be equal to V of R2 would be equal to V of S. All of the, basically this voltage is equal to this voltage is equal to this voltage here. They are all electrically common. So of course then over here basically the current is going to be different, meaning that the current, if I call this I of t, then basically that you would have I2 over here and I1 over here, and then in this case basically I1 plus I2 would be equal to I of t, right? So that is basically that. Now to answer the question that we had before, basically we had this circuit over here, and to answer the question what is the voltage drop across R2, you can just simply calculate the total resistance in this circuit R of t, which is equal to R1 plus R2 plus R3 plus R4, which is equal to 10 ohm, which plus 20 ohm plus 50 ohm plus 100 ohm, which is equal to 180 ohms. Which is equal to 180 ohms. That's your R of t. Now the voltage drop across R2, V of R2, based on the formula that we derived below, was basically R2 to R of t times V of S. And over here we have the power supply is 6 volts, 6.0 volts. So V of R2 therefore would be equal to R2, which is 20 ohms, divided by basically 180 ohms, times V of S, which is basically 6.0 volts. Ohms and ohms you can cancel out. That would be 2 to 18, which is 1 to 9. So that's 1/9 of the power supply voltage, which is basically something about basically 1/9 times 1/9. I'm not very familiar with this calculator, what it does with the numbers. 1/9 times basically 6. It's the same thing as 2/3, and 2/3 is the same thing as, of course, 6 times 1/9 is basically 6 times 1/9 is 6/9. 6/9, and 6/9 divided by 3, you'll get 2, divided by 3, you'll get 3. 2/3 is the same thing as 0.6666. Taking two significant figures, you would get basically 0.67 volts, right? 0.67 volts, which is the same thing as 670 millivolts. 670 millivolts. So that's basically one typical circuit that you should be basically familiar with in your work. Otherwise, in different circuits, you would run into problems, right? Now, the next thing that we need to know, and I have said this before, but I will repeat this for those who are basically following these videos and don't know what's going on in these videos or why I'm doing these videos. I'm essentially doing some basic electronics course. I'm essentially doing some basic electronics course, which is more towards basically the practical side of electronics, which is more geared towards the practical side of electronics. Of course, over here we are all talking about theory, but this is not much theory. This is simple algebra and some rules related to DC and AC circuits and things like that. We are not really even using calculus here. So why I'm doing this is basically primarily I want to, hopefully in the near future, I want to be working on some power supply circuits, some basically some transistors, some theory and practice related to transistors, and probably some vacuum lamps, and also but mainly about radios. Meaning that I want to basically put this whole course together, everything that you need to know in order to be able to understand radios and build your own radio and understand the theory behind the radio and all of the circuits that you need to build in order to build a working practical radio. And then if time allows us, we will also talk a little bit about, for example, how to basically transmit data over the air using a radio, which is essentially your cell phone or your wireless LAN, for example, a router at home. That's what it does. It's transmitting data over the air. That's what we will talk about. But then that would be something related to, that would be a course that we would have to do, and then for that we would need to talk a little bit about some programming and IT concepts and computers and that sort of thing, and about, for example, some electronics engineering, something like that, put the whole thing together to understand how basically how data is transmitted over the air in telecommunication, or at least small scale, to understand that, right? So that's basically why I'm doing all of these videos. Otherwise, and of course they are mainly fun. I mean, from my very childhood, I was very interested in electronics, but never actually did the theory. So now I have the opportunity to do that. So, okay, so that was the second question. Okay, so now in the same circuit, if you want to, for example, calculate the voltage across, for example, across R3 and R4, so you can see that R3 and R4 together would be 150 ohms, right? So we know that basically our R of T is equal to basically 180 ohms. I erase all of this. So our R of T is equal to 180 ohms. R of T is equal to 180 ohms, all of the resistance in our circuit. And the voltage across these 2 points, call it V1 for example. This voltage is basically the sum of the voltage across R3 and the voltage across R4, the sum of these two voltages. So you can regard these two resistors as just 150 ohm resistor, and then write the same basically equation for these two resistors, meaning that you can say that V1 is the same thing as basically R3 plus R4 divided by R of T times basically V of S, which is the same thing as 150 to 180, both in ohms, right, times V of S, which is basically 6 volts. And these two will be cancelled out. There you have basically 15 to 18, which is basically divided by 3, you'll get 6, divided by 3, you'll get divide by 3, you'll get 5, divide by 3, you'll get 6, 5/6, and 5/6 is the same thing as 0.8333, and so on and so forth. So there you have basically there you have basically 5/6 of times basically 6.0 volts, and 6 and 6 you can cancel out. You will be left with 5.0 volts. So the voltage that you would measure across these 2 points would be a 5 volt voltage, right? So that's basically, I think now you have understood this kind of circuit. So now let's go and do another question. As another question, let's say that you have three basically resistors connected in parallel across a battery. For example, you have this resistor over here, and this resistor over here, and this resistor over here, all connected across a power supply, a battery. So this comes to a power supply. Let's say that this is your power supply and that is your circuit. Now R1 is equal to, let's call it R1, call this R2, call this R3, and let's say that R1 is equal to 470 ohms. R2 is equal to basically 2.2 kilo ohm, 2.2 kilo ohm, and R3 is equal to 3.3 kilo ohm, right? Now what is the voltage across R2? V of R2. So in this circuit, and this is, let's say that this is the voltage, 15 volt for example, V of S is equal to 15 volts for example. So the voltage across, you can see that the voltage across the power supply is the voltage across these points A and B, right? And B is electrically common with this point, with this point, with this point. A is electrically common with this point, with this point, with this point. Which means that basically R1 is directly across the power supply. R2 is directly across the power supply. R3 is directly across the power supply. Which logically means that the voltage across R1 is the same voltage across the power supply. The voltage across R2 is the same voltage across the power supply. And the voltage across R3 is the same voltage across the power supply. That's basically what parallel circuits are, or what they do. Which means that V of R1 is equal to V of R2 is equal to V of R3, which is equal to V of S. That is because you have a parallel circuit. You have a parallel circuit, right? So that is basically another question. These questions are essentially simple, but sometimes if you don't know the concept, of course they get you thinking a little bit, but then once you solve the problem, then you have learned the concept, right? So now the current, for example, if you want to, if I call these, for example, if I call this I2, for example, I3, and if I call this I1, for example, now what is the current going through R2, for example? The current going through R2 is basically a parallel circuit, is essentially like your house, like the electric wiring system in your house, meaning that in your house there is a point where basically power comes in, and from that point it is basically distributed all across the house. Now suppose that, for example, in your house you have basically this room over here, you have another room over here, you have another room over here, and you have another room over here. You have 4 rooms in your house, and this is the mains coming in. So what happens is that they usually put a terminal in somewhere where the terminal is the closest to all of the 4 rooms. For example, suppose that this is the I don't know what is the schematic for a terminal is called. Let's just say that this is the terminal, and then this terminal is connected to your mains, meaning that your mains simply comes and is connected to your mains, meaning that now your mains is over here, and now there is basically a terminal for this room. Then there is a terminal for this room. Then there is a terminal for this room. Then there is a terminal for this room, right? And then from this terminal, you will basically connect these wires to the mains here. Or actually they should be connected to the terminal directly here, but for the sake of simplicity, I'm connecting them directly to the mains here. Also here, also here. So, and also here, and also then here, and also here. And now all of these terminals are connected to the mains. Now suppose that you have a lamp in this room, right? The lamp is for example, through a switch, is again connected to these 2 wires. Suppose that there is another lamp in this room, and the other lamp is again through basically a switch is connected to these 2 wires. Suppose that there is a lamp in this room. This lamp is again connected to the terminal for this room. There is another lamp over here that is also connected to the same terminal in this room. And of course they put a switch for each of these lamps so that you can turn them on and off. There is a lamp over here. You can connect it to the terminal for for this room. There is a lamp over here. You can connect it to the terminal for this room, and so on and so forth. So as you can see, each of these lamps is essentially, at the end of the day, is parallel to the mains, meaning that the mains comes over here, is connected to this lamp. The other end of the lamp goes to the other end of the mains. This lamp over here is connected to this point, connected to this point, connected to this point, and the other end would go to this point and this point and this point and this point. So the mains is parallel to each of the appliances in your house, right? Which means that if I want to simplify this circuit, I would say that I have the mains over here, and if I have a lamp over here in one of the rooms, that lamp is connected to the mains, right? That lamp is connected to the mains. That is lamp number 1 for room number 1. Suppose that I add a room to my house, and for this lamp, again, I need power. So I simply connect it to the same 2 wires. And again, I have light over here. I have another lamp for another room. I connect it to the same 2 wires. I have another lamp for another room. I connect it to the same 2 wires. And then I will end up with a parallel circuit, right? Now, suppose that there was only one lamp in my circuit, right? Suppose that there was only one lamp in my circuit. Now the current going through this lamp you could simply calculate it. P is equal to VI. So if suppose that, for example, this is a 100-watt lamp, that's and your supply voltage is 220 volts, so times I, so I would be equal to 100 watts divided by 220 volts, which is the same thing as basically 10 to 22, which is the same thing as 0.45 amps, or 450 milliamps, right? 450 milliamps with 2 significant figures, of course, but that's not really important here. So, which means that when I have basically one lamp in my circuit, 450 milliamp, I is equal to 450 milliamp of current is going through my circuit. Now you can do this experiment using a simple, for example, 12 volt power supply. Put a basically 12 volt lamp on your power supply, and on your power supply there is basically a needle or a basically a amp meter that shows you how much current is being drawn from your power supply. You will see that, for example, some half an amp, for example, is going through your circuit depending on your lamp, the type of your lamp. Now you can put another lamp in the circuit on the same 12 volt power supply, meaning that put the second lamp over here, and if it is the exact same lamp with the exact same power rating, if in the first instance you got, for example, 0.5 amps going through the circuit, once you add the second lamp, the current jumps up to 1 amp, because this is 0.5 amp plus 0.5 amp is equal to 1 amp, right? And add the third lamp, then basically 1.5 amp basically would be going through the circuit, and so on and so forth. That means that basically if I call this, for example, I1 and I2, and basically, for example, over here I3 and all the way up to I of n, the currents going through each of these branches is going to be the sum of these currents, I1 plus I2 plus I3 plus all the way up to I of n is going to be equal to I of t, right? That's basically how the current behaves in a parallel circuit. So that basically means that basically then the current going through now the question here was, I forgot the question. What is the current through R2, for example? Through R2. So through R2, you can simply apply the Ohm's law to R2 in this circuit and calculate the current going through R2. Because the voltage across R2 is the power supply voltage, so V of R2 is equal to 15 volts. And R2 is equal to the value of the resistance is basically 2.2 kilo ohms, right? Which means that basically the current going through R2, that what is I of R2, so then you know that V is equal to I times R. That means that I is equal to V to R. That means that I is equal to V, which is basically 15 volts, divided by R, which is 2.2 kilo ohm, which is 2.2 into 10 raised to the power 3 ohms, right? Which gives you basically something like, I don't know, 15, that's about 7 milliamps, I suppose, right? 15 divided by 2.2 is 6.8. That is basically 6.8 into 10 raised to the power negative 3 amps, which is basically 6.8 milliamps, right? So that is basically the current that is going through, for example, this resistor over here. Very simple. And now in the same circuit, so now we know that basically I of R2 is equal to 6.8 milliamp, right? Now in the same circuit, how would you calculate the total current going through your circuit? We will do an experiment here. That would actually be interesting. Okay, so now what we did was that we calculated the current going through R2, which was 6.8 milliamps, right? Now what we will do is that we will calculate the current going through R3 and R1 as well, and then we will basically add them together, meaning that for example for R3, you know that R3 is equal to 3.3 kilo ohms, and the voltage across that is V of R3 is equal to the same 15 volts. So that means that if I is equal to V to R, right? If I is equal to V to R, that would be equal to 15 divided by 15 volts divided by 3.3 into 10 raised to the power 3 ohms. And that would be basically 15 divided by 3.3 would be equal to 15 divided by 3.3 is equal to 4.5 basically into 10 raised to the power 4.5 into 10 raised to the power negative 3 amps, which is the same thing as 4.5 milliamps. So that means that I of R3 is equal to 4.5 milliamps. And we know that basically the value of R1 is 470 ohms. The value of R1 is equal to 470 ohms. And so V of R1 is the same 15 volts. So I of basically R1 would be equal to V of R1 divided by R1, which is the same thing as 15 volts by 470 ohms, which is the same thing as 15 divided by 470 is about 30 milliamps, 31 milliamps or 32 milliamps. So I take that as basically 0.032 amps, which is basically 32 milliamps. So that means that so basically I of R3 is 4.5 milliamps. 4.5 milliamps. I of R3 is 4.5 milliamps, and I of R1 is 32 milliamps. I of R1 is equal to 32 milliamps. And as you can see, as the amount of resistance basically decreases, you can see that, for example, for the current going through basically that's actually not 32 milliamps, but that is basically, that is the same thing as I made a mistake here. That doesn't make any sense. So this is basically 3.2 into 10 raised to power negative 2 amps, which is the same thing as basically 32, which is the same thing as 32 into 10 raised to the power negative into 10 raised to the power negative 1 into 10 raised to the power negative 3 amps, which is equal to 32 into, that is tube actually, into 10 raised to the power negative 3 amps, which is the same thing as well, 32 milliamps, of course. So now 32 milliamps here, that is correct. So you can see that as the amount of resistance goes up, so over here the amount of resistance is 2.2 kilo ohms, and on the same power supply, on the exact same power supply, when the amount of resistance is about 2 kilo ohms, the current going through that resistor is only 6 milliamps. But then when the amount of resistance goes down, the amount of current goes up, meaning that it becomes 32 milliamps, is about 5 times that current, right? So now what's important here is that you can actually now that the experiment that I wanted to do here is that now you know that the current going through each of those branches, meaning that you know that basically through this branch, for example, 32 milliamps of current is flowing through this branch, and so on and so forth. Now I could have solved this problem in a different way, meaning that I could have said that basically, okay, so I will calculate the equivalent resistance in this circuit, and I would have basically regarded this circuit as only one resistor and one power supply, and then that would be the same V of S is equal to 15 volts, and this would have been R of t, and some current would be flowing over here, I of t, for example. Now to calculate these resistors, okay, so to calculate those resistors, what you can do is, of course, simple, meaning that you can basically the formula for these resistors would be taking basically 1 over R of t is the same thing as 1 over R1 plus 1 over R2 plus 1 over R3 because they are parallel resistors. And so then you have basically the parallel resistance here is basically you have to write this as 1 over 470 ohms, 1 over 470, and then if you write this in ohm, you have to write everything in ohm, plus 1 over, for example, 2.2 into 10 raised to the power 3, for example, plus 1 over basically 3.3 into 10 raised to the power 3, and then, for example, give this to a calculator to calculate it for you. One more way to do it, which is of course simpler, is that you can go to basically all about circuits. So for example, you can go to parallel resistors calculator, all about circuits. All right. So if you go over here and suppose that you have the number of resistors, as 3, for example, and then you have it didn't change actually, it should have changed. Okay, so what we can do is that we can take two at a time, for example, meaning that you can imagine that you have, for example, these two resistors in parallel. Let's calculate R2 and R3 first. So for example, this is 2.2 and 3.3 kilo ohms. So I make it 2 basically, make it 3. Okay, that gives me, so this is supposed to be in ohms, so that's basically 2.2 kilo ohms would be 2,200 ohms. 3.3 kilo ohms is 3,300 ohms, and the other one is 470 ohms. Calculate, you'll get 346.59. 346.59, right? So that means that your R of t here is actually 346.59 ohms in ohms, right? So now I know that my R of t here, basically R of t is equal to 346, take basically not more than 3 significant figures, 346 ohms, for example, and V of S is equal to 15 volts. And so the current going through the circuit would be I is equal to V to R, which is equal to 15 to basically 346. This is in volts, this is in ohms, so that you should get something in amps. And if you divide basically 15 by 346, that gives you 0.043. That gives you 0.043 in amps, which is 43 milliamps, right? So that's the total current going through this circuit based on this calculation is 43 milliamps. Now if you add these currents that we calculated through each of the resistors together, I'll have 32 milliamps. I have 6.8 milliamps, I have 4.5 milliamps, and so I have basically over here 13, 1, and then 10, 13, 1, and 43.3 milliamps. The exact same current that you calculated here is the total current actually going through this circuit. Right? So now, of course, you would round this to two significant figures, write it as 43 milliamps, and so you would get the same current here. So that means that basically in a parallel circuit, the sum of the currents going through each of the branches is basically equal to the total current going through the circuit, right? That's basically what I wanted to show you here. So in the next video, we will continue with these exercises. We have a couple more exercises here. Now there is actually one more part to this question. Let me finish this part, and then we will end this video. So in this example, in the exact same example, suppose that resistor R2 opens up, meaning that you cut this wire over here, and resistor R2 is out of the circuit, right? So now what would happen to the current through the other two resistors? Meaning that if you do not open this up, meaning that if it were actually connected, so of course 32 milliamps would be flowing through R1, 6.8 milliamps would be flowing through R2, and 4.5 milliamps would be flowing through R3, right? Now suppose that, for example, for whatever reason, I cut this open. If I cut this open, the resistor R2 is not in the circuit anymore. Now what sort of change would that have and the current going through the resistors R1 or R3, right? Now if it was a series circuit, so for example, suppose that you have a series circuit over here like this, and if I have R1 and R2 and R3 over here, if I cut this resistor, for example, R1 from here, the current through the whole circuit drops to 0 because the circuit is now open, right? Or suppose that, for example, I shorted this resistor R1 like this. So since the amount of the resistance in the circuit now drops, you have less resistance in your circuit, so then the current going through the circuit would increase, right? So this is a series circuit. But in a parallel circuit, what happens is that when R2 is not in the circuit anymore, it has basically no effect whatsoever on the current going through R3 or R1. The same current that was previously going through R1 or R3 would still be going through R1 and R3 because basically R1 is essentially connected to power supply. It's still drawing the current that it was drawing before. R3 is still connected to the power supply. It's drawing the current that it was drawing before. The only change is that R2 is not in the circuit anymore, meaning that R2 is not drawing any current, but the current through R1 or R3 would not actually change at all. There would be no difference on those two currents. So that was basically a couple of questions on current through DC circuits. We will continue this. I think we will need one more video to basically to finish these questions. I'll see you in the next video, and thank you.